Welcome. In this video, we will talk about how to use polynomials to approximate some complicated function values. Let's start with an example. Let's think about estimating the value of the square root of e. We could write this as e to the 1/2 power. Now, e is a transcendental number. It's approximately equal to 2.71828, etc., etc. We could just plug this into a calculator and we'd get a decimal approximation, but how could we estimate the square root of e if we didn't have a calculator? And what is the calculator actually doing to estimate the square root of e? Well, we will see how to estimate this value using something called a Taylor polynomial. We know from previous sections that e to the x can be expressed as a Taylor series. It's the infinite sum, where n goes from 0 to infinity, of x to the n divided by n factorial. A Taylor polynomial is a truncation of the Taylor series. Instead of taking an infinite number of terms, we stop at some degree. If we take the 4th degree Taylor polynomial, we denote that by t sub 4 of x, and we take all the terms up to degree 4. So this would be the polynomial 1 plus x to the first divided by 1 factorial, plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, and then finally x to the 4th divided by 4 factorial. This is the 4th degree Taylor polynomial for the function e to the x centered at 0. This is an approximation for e to the x. So if we would like to estimate the value of the square root of e, that's the same as e to the 1/2. E to the 1/2 power is approximately equal to the value of this polynomial when x equals 1/2. If we plug in x equals 1/2 into the polynomial, notice that all of the arithmetic operations are multiplication and addition. We're simply multiplying 1/2 by itself when we raise it to the powers, and then we're adding these terms together. So to estimate this complicated value of e to the 1/2 using a polynomial, all the operations involved are addition and multiplication. Let's take a look at what this value is in Desmos. Here we have the plot of e to the x. And if we plot the 4th degree Taylor polynomial, we get this function in blue. Notice how close these two functions are, especially around the value x equals 0. We're using this 4th degree Taylor polynomial to estimate e to the 1/2. We're evaluating the polynomial when x equals 1/2. And we get a value of approximately 1.648, etc. Let's compare that to the true value of the square root of e. That's 1.6487, very, very close. In fact, these two values match up to the 1,000th place. In other words, our 4th degree polynomial gave us a very good approximation for this complicated transcendental value of the square root of e. Now we would like to know how close is our approximation. Without actually computing it, can we find estimates for how far off our approximations are from the true values? Well, we measure the error in these approximations using something called the remainder. We denote it by r sub n of x, and that's the true value of the function minus the approximation given by the Taylor polynomial. A good way of thinking of this r expression is to think of it as the error involved in the approximation. There is a way to bound the error in these approximations using something called Taylor's inequality. Taylor's inequality provides an upper bound on how bad the error is. In other words, it guarantees us that our approximation is within some value of the true number that we're trying to approximate. In class, we'll learn more about Taylor's inequality and how to use it, and we'll see that for a better approximation, we use a higher degree Taylor polynomial.